So I'm Joris. I'm working at Photon Data. We are a company building large-scale data analytics, petabyte scale, specifically focused on a compute engine on using GPU. But a lot of that is built on top of the Apache Arrow project. And essentially, Photon Data allows me to work on Apache Arrow to maintain some of the parts of the Apache Arrow project. And so I will try to give you some introduction to Apache Arrow and some new things that are going on there. Quickly as a question, like who in the room would feel familiar with, like, would say that they can explain what Apache Arrow is? More than I expected, but still a large minority. So I will try to also give an introduction to Arrow. My slide is not moving. Yeah, I'm also involved in Pandas, in GeoPandas, some of the other open source packages. But Apache Arrow at the core is all about an open standard. And so my slides are HTML slides, and they work in different browsers because HTML is a standardized markup language. So it's very important for interoperability between different systems to be able to work together. Of course, Apache Arrow is not about a markup language, but is about how to represent data in memory. And to make the analogy there, like more closer to data, is if you have an array. So you see here on the left an array, a 2D array with some numbers, and the way that this is typically, or most languages will store that in memory, is as a single contiguous buffer somewhere in memory. And so if you point to the start of that buffer and you give some information about the data type, the length, the shape, almost any language will be able to use that data directly. And so in Python, this is standardized as the buffer protocol, and a large part of the scientific stack, the PyData stack in Python, is built on top of being able to share data like this, like zero copy, directly sharing data of arrays. And so Apache Arrow is then essentially generalizing this idea, but not for a single array, but for tabular data, so for tables, data frames. So instead of a single array, we will have multiple columns with different data types. Those columns have names, we have more complex data. So it gets a bit more complex than this single buffer. In context of data frames, of tables, more traditional databases will typically store that data in memory in a row-wise fashion. But Arrow, and certainly most of the more modern data systems, will store data columnar. So it means that all the data of one column is stored together in memory. And so Arrow is essentially for that kind of columnar data, a standard to how to represent that data in memory. This is, I'm not going in all the details of this figure, but what you see here essentially on the left, you see a column, one array, and in this case it's a nested data, so it has some list values. So that's how we think about a potential, in this case, nested data type, a column in a data frame. And then what Arrow does is essentially it specifies like how are we going to represent that in memory. And where for a single array we had a single buffer, in this case we will have multiple buffers. Because we have one buffer, and so on the right you see the different buffers that is needed to represent the data as how we think about it on the left. We have a buffer for missing values, we have a buffer for the actual data, because it's nested here. And so Arrow will essentially describe like this buffer layout for every possible data type that you can think of, including variable with data, nested data, structs, but also support for missing values, etc. Why is this important? I already mentioned interoperability, but so one of the driving use cases for that Arrow has started was to make it easier to interchange data, to move data from one system to another. So if you're using different languages and you want to move data from, for example, from R to Python, or from Python to some C++ library, in the past, a lot of conversion, custom methods to convert from one to another happened, being less efficient, being more work to implement. And so if all those tools understand Arrow memory, we can much more easily move data from one system to another, or share implementations, for example, to read a certain file format. And so this figure here, this diagram, is a diagram that was created at the start of the project of Apache Arrow in 2017. You can notice from the names on it that it's indeed an old diagram. Nowadays, we'd probably put things like Snowflake or BigQuery or other things in there. So then it was a vision, but in practice, nowadays it's essentially become a reality, and most of the data systems nowadays use, or at least have the ability to use Arrow as an interchange method. It's not only about moving data around. Arrow is also meant to be an efficient format to process. Getting back to this columnar aspect that I mentioned, so it's laid out in memory efficiently, so we can process it efficiently, and so it's not the focus of this talk, but there are quite some of the more recent compute engines, data frame libraries, databases that either use Arrow directly, for example, Data Fusion using Arrow Rust, or is built on or uses internally something that is very compatible to Arrow. So Apache Arrow, the core of Apache Arrow is so this standard about how do we represent columnar tabular data in memory. But there are also a bunch of other specifications on top of that, how defining standard ways to share the data in Arrow formats. And there are also a bunch of implementations. The same as a figure, so we have a whole bunch of implementations in various languages. I think most languages that you might want to use have an implementation of Arrow. They all implement at least the specification, but some of them also provide a whole set of toolboxes to work with Arrow data. For example, I work on PyArrow, which has bindings to the Arrow C++ library. And PyArrow, in addition to just implementing the formats, also comes with a reader for Parquet. It can read from cloud systems. It has some computes, a whole set of tools to work with Arrow data. On the specification side, at the bottom, so the core is this columnar format, as I mentioned before, and on top of that, there are some other specifications. So there is something about sharing data within the same process. I will get into detail about that later in the talk. There is an IPC, inter-process communication format, for very lightweight serialization if you want to move data in Arrow format from one process to another or move it over the network. So it's a very lightweight serialization, avoiding as much as possible copies in the process of this serialization. Flight builds on top of IPC, providing a network protocol for client-server applications focused on using Arrow data in the application. ADBC for standardized database access. I will also get back to that later in the talk. So for the remainder, this was the not so very short introduction to Apache Arrow. And for the remainder of the talk, I want to highlight some of the newish from the last 2 years developments in the project. This is an overview. I won't have the time to go in detail on all of them, but so there are a few additions to the columnar format itself. So there are some new data types being added. There are some additions to the C data interface. I will get directly to that as well. The IPC format, so the serialization format, there is an experimental new feature. So typically, essentially the IPC format consists of a small header with some metadata, and then all the data of your table itself together. And traditionally, that needs to be put together in one message and sent over over the wire to some other process. So there is an experimental support to be able to send the metadata and the actual data itself separately, so that the data itself can use a different kind of memory. It can live on a certain device instead of having to be copied to the CPU, using shared memory or some other transport mechanism. Arrow flight has been marked stable. ADBC has been expanding, but I will get to that later. There are also some newer implementations. So nanoarrow is a small library meant to be like implement just the basics. It's in C. It's easily venerable. If you want to, instead of depending on one of the bigger implementations, you want to have some access to just the Arrow data format itself, you can use nanoarrow. There are some other projects outside of the Apache Arrow project itself. For example, Sparrow being developed by Quantstack people that are present here, that potentially has some similar goals as nanoarrow. I will skip that for time. First, some newer additions to the columnar format. I find an interesting one. It dives a bit deeper into how one of those data types actually work. And so it's specifically for the string data type. And for that, we first need to understand how strings are stored in Arrow traditionally. So what you see here on the left, again, is a column with some string data. So it's an array of the string data type, and that's how we think about our column in our table, how it's being stored in memory, the 3 buffers that you require for this, you can see on the right. So we have a buffer for missing values. But essentially, the most important part here is that all the strings that you see on the left side, so all those strings, they are stored consecutively in one single buffer in memory. And that's the values buffer that you see here on the right. And then to know, where a certain value, for example, the first value here, where that's stored in that values buffer, we can say, okay, it starts from 0 up to 6 in the offset into this values buffer. So we have the buffer storing those offsets. So for the first value is from 0 up to 6. The second value is from 6 up to 10, etc. So we store those values consecutively in a single buffer. That's very memory efficient, but it also has certain downsides. And one of them is that it typically will, you have to copy the values buffer a lot if you do certain operations. For example, if you do a filter operation where you filter certain, you drop certain values, or you do a sort operation where you essentially just reorder values, because our strings in the values buffer needs to be consecutively, every time we do an operation like that, we essentially have to rewrite the whole values buffer. And that's so one of the big downsides here. And for that reason, people have been thinking about a better way to store strings in memory that addresses some of those issues. Again, on the left, you see some strings. Yeah, I should have taken the same ones. That would have been easier. But so these, again, are the strings that we have in our column. And on the right, you see how it's stored in memory. And the main aspect about this one is that we have a views buffer. So you have the views buffer here. And this stores some additional information about our strings. So it always starts with the length of our string. So for the value of short string that we have here, we store the length of the string. And then we also store either the full string itself, if it's a short string, or in the case next to it, we store again the length. We store just the first few bytes of the string, and then we store an index and offset where the full string is stored. So in this case, it says, okay, this string, you can find it at offset 21 here in our values buffer, and we know that the length is 19, so we know exactly which string it represents. And so we have this fixed width buffer, the views buffer, where we store the length, a prefix, and so these, if it's a longer string, then an offset to where the string lives. So we have the benefit of having this fixed width buffer, which is more efficient to work with. In addition, because it just points to a certain location in the values buffer, this values buffer doesn't need to be nicely in order consecutively. So at the example that I gave before, if we would reorder, we do a sort operation and we reorder our column, the only thing that we have to reorder is this views buffer, which is a fixed width buffer, which will be more efficient to reorder. But all our strings itself, because we are just pointing to the offset in that values buffer, we can just leave as is. And so we will get a lot less copies involved here. So yeah, it's originally developed and written about at TU Munich. So it's also sometimes referred to as German-style strings. It's used already in some of the database systems. It was added to the Arrow columnar format. There are some, it gives some optimization possibilities, so it will involve less copying of data, as I already mentioned. Because of the prefix, you can do faster comparisons, because you can first check the length and the prefix. And so if you want to read more about that, you find here 2 blog posts that, from projects that adopted it, telling about their experiences. That was very short about one of the new data types. Another thing that I want to mention related to data types are extension types. And essentially an extension type is that, you can annotate an existing data type with some custom application-specific metadata. You can give it a name and some metadata to store with it, to essentially, expand the set of data types that Arrow provides. And over the last year, a bunch of those types have been standardized. And for example, like fixed and variable shape tensors, we essentially just store the actual values of those tensors under the hood, but the extension type then you can, in the case of the fixed shape tensor, also store what is the shape of your tensor, so you can have interoperability with, things like PyTorch that work with tensors. Also JSON, UID, 8-bit Boolean is another example where Arrow, the Boolean type of Arrow uses single bits, but for example, QDF, which is mostly Arrow compatible, but one of the differences is that they use Booleans with 1 byte, so 8 bits, and so that allows them to still share data with another system without any copy. I also want to mention, because I'm involved here, an extension type from the community about how to represent geospatial data in Arrow. So the GeoArrow project is standardizing that. Okay, that was about the core columnar format. I want to move to the Arrow C data interface. And let's just start with an example. So I have a polars data frame here, and a polars data frame has a 2-arrow method. It returns a PyArrow table, and assume that I want to move my polars data frame to Data Fusion, another data frame library based on Arrow. And so Data Fusion has a from Arrow method, so I can pass that PyArrow table to the from Arrow method, and I get a Data Fusion data frame. I can also then convert that back to polars if I would like to. And so all those conversions are completely zero copy, so very efficient. And they're zero copy because those Rust libraries and the C++ library for PyArrow, they essentially just point to the same data in memory. The way that this works is through the C data interface. So it allows sharing data between different libraries, between different implementations within the same process. And that's the limitation, it has to be within the same process. Essentially, it's a C-struct, a stable ABI, and not go into the details here, but essentially we point to the start of those buffers, just like the buffer protocol in Python, and then with some additional metadata that allows us to interpret those buffers. Now going back to this example, the problem with this example is that we, as a user, still have to call this to-arrow table, and so we need to be familiar with, exactly which methods, which clearly differs between different libraries, do we have to call. And in addition, we are moving data from polars to data fusion, both implemented in Rust, but here we are actually first passing the data through PyArrow through a C++ implementation, while we can directly share the data between polars and data fusion as well. And so recently, for the last, with the last releases of those libraries, we can actually remove those to-arrow table methods, and that will work out of the box as well, like this. And how does this work? That's thanks to the PyCapsule interface, which is essentially a Python layer on top of the ROC data interface. So a capsule is a standard library Python object to share a pointer through the Python layer. And then we have some dunder methods, so with a double underscore, that makes that people can recognize, libraries can recognize other objects. So in the case here of this data fusion data frame, has a dunder method, a dunder ROC stream method, and so the polars data frame constructor, if it gets an object, it will check, has this object this specific dunder method? And if it has that, it knows that that object can convert itself to Arrow through the ROC data interface, and I can consume that data 0 copy. And so, whenever an object has this ROC stream method defined, it knows it can provide me a stream of Arrow data. And just to, it's a bit of a ridiculous example, but it's possible. It's code that runs if you use the latest versions of everything. So I start with the pandas data frame. I pass it to DuckDB. The DuckDB result, I move it into a polars data frame. I convert that to a PyArrow data frame, and then the PyArrow data frame to a table to data fusion and back to pandas, and that's all under the hood automatically using the ROC data interface through this PyCapsule protocol. Not that you should do this in practice, but if you're working, for example, with two libraries, two of those, that works nicely. And I could also have added more data frame libraries, but yeah, my slide was not longer. So that's very briefly about the capsule interface, improving interoperability between different data frame libraries in the Python ecosystem. The device interface, very briefly, the ROC data interface is focused on CPU data. So this extends it a bit to non-CPU data. For example, if you have data on a CUDA GPU and you want to share that data between two different libraries, then there is now also an extension allowing that. I won't have time to go into detail on this last topic, our ADBC or our database connectivity. But essentially, making it very short, is that there are existing tools that you can use. For example, JDBC, ODBC, or the Python database API, where you have like a generic API that can work with multiple databases. The drawback of most of those is that they are all based on the results that you get are based on getting data row by row. That's certainly if you want columnar data, with Arrow, that's a lot of overhead going through row-oriented data. And so ADBC is essentially similar as those other protocols, but providing you Arrow data. And so ADBC, it's Arrow native. You get data in Arrow format based on this C data interface that I explained before. And it's, backend agnostic, so you can have driver implementations for ADBC for any possible database. And so there are already implementations of drivers for a whole bunch of data frames, and the most recent that was added was Google BigQuery. You also have a bunch of libraries in languages using those drivers, so you have native interfaces for each language to work with these drivers. And so, for example, in Python, that's the DB API. So there is, for all those drivers, you have a Python interface using with a traditional connect, cursor, execute, and then just instead of fetching a single arrow, fetching a single row or fetching all rows, there is a fetch arrow table method that gets data in the arrow format. And this can, because it avoids the overhead of row-wise data, it can give a very decent speed up in connecting to databases for the use case of getting bulk data in Arrow format. Voilà, that was a bit fast for the last part, but I'm very happy to further chat about it afterwards.
Thanks. Thanks, Joris. So is there any questions? Yes.
Hello, thank you for the presentation. A very naive question from a data frame end user. I understand that there is a competition now between Rust and C++, and there is a C++ PyArrow implementation, which is used by Python. Will there be a Rust-based PyArrow Arrow implementation for Python?
So I go back to where was it? So there are actually already, so Data Fusion is a Rust compute engine on top of the Arrow Rust library. And Data Fusion has Python bindings. So that's already one way to use Arrow Rust, essentially. There is also a library called Arrow 3 from because the way to connect with Rust, there is a PyArrow3 library, so that's essentially using PyArrow3 to connect directly with Arrow Rust, so not with Data Fusion, but just with Arrow Rust itself. So if you want to have some functionality from the Arrow Rust library exposed in Python, then Arrow3 is an option as well.
Hello, congrats for your talk, quite nice one. What's the motivation for using 8 bits for Boolean data?
You will have to ask someone who develops QDF. I'm not entirely sure. It might be that, specifically the APIs that they have available for CUDA, are less efficient for working with bits. No idea.
Any other questions? Okay, here.
Yes, thank you. Can you speak about Parquet and PyArrow and the relationships between them?
Yeah, that's a good question. It's something that is often confused. So Arrow is a standard about how do I represent data in memory. Once I have a file format, I load it into memory, how do I represent that data? Parquet is a file format. And they are closely related in the sense that often Arrow implementations have a Parquet reader and writer. And the reason for that is because Parquet is a very well, there are very nice complements because Parquet is also a columnar file format. And it's, if you want to efficiently work with Parquet files, you will typically load it into Arrow memory. But so Parquet is the file format. It's optimized for that use case. It has a lot of advanced compression and encoding options to get as small as possible files on disk while still being efficient to read from. That's the file format. Arrow is the in-memory format.
That basically answered my question as well, but good talk. Thank you very much.
Thank you.
So we still have time for one question if someone wants. Yes.
Okay, so what about Feather and Arrow on disk?
Yeah, that's the next part of my answer to the previous question. You can, the Parquet is a file format, Arrow is an in-memory format or something that you share over the network. You can, of course, whatever you have in memory, you can also just dump to the disk and have a file. And that's essentially what Feather is. It was something that was used, or one of the initial applications that they implemented at the beginning of the Arrow project to showcase the usefulness of it. But so in general, right now, if you still would like to use Feather, or essentially it's the IPC, it's the serialization format, but dumped to disk instead of sending it over the network. It's faster if you have a very fast disk connection. It will be faster to read from IPC than from Parquet. And so there are certainly use cases for it, typically for temporary data, for spilling data temporarily, for example. But Parquet is much more like if you want smaller data because you want to store them, a lot of data, then Parquet has a lot more advanced options to compress data, etc. So that's one of the differences between both.
Okay, so I think we can stop here. If you have more questions, you can ask Joris during the breaks. And we can thank Sims